Welcome back. In this second part of Module 1, Lecture 3, we'll continue exploring the foundations of Lean Six Sigma, a structured approach to improving quality, reducing waste, and driving efficiency across operations. Let's dive in and see how these principles apply to real-world manufacturing and service processes. The cost of poor quality, or COPQ, represents all the expenses an organization incurs because processes aren't performing the way they should. These costs show up in many forms: scrap, rework, warranty claims, delays, and even lost customers. Poor quality drives operational expenses up, often dramatically. But when organizations reduce COPQ, they improve efficiency, strengthen customer satisfaction, and ultimately increase profitability. Understanding COPQ is essential because it shows why quality improvement isn't just a technical effort, it's a financial strategy. Let's look at how the cost of poor quality, or COPQ, appears in a real manufacturing example. In the bearing housing process, poor quality leads to several types of cost. Scrap. Defective housings must be discarded, wasting materials and labor. Rework. Additional machining is required to fix parts that don't meet specifications. Inspection. Extra inspection labor and downtime add to production costs. Warranty. Returned assemblies and customer complaints increase service expenses. Lost business. Reduced customer confidence leads to fewer future sales. Each of these costs directly impacts profitability. By identifying and reducing COPQ, organizations can improve efficiency, strengthen customer trust, and enhance long-term performance. A SIPC diagram is one of the first tools we use in the define phase of DMAIC. SIPC is a high-level process mapping tool. It helps us step back and look at the process from a broad perspective before we get buried in the details. The letters in SIPC stand for suppliers, inputs, process, outputs, and customers. Suppliers are the people, departments, or systems that provide something to the process. Inputs are the materials, information, or resources needed for the process to work. The process is the set of major steps that transform the inputs into outputs. Outputs are the products, services, or results produced by the process. Customers are the people or groups who receive those outputs. The value of a SIPC diagram is that it helps the team clearly define the boundaries of the process. It also helps identify the key stakeholders who are involved or affected. In Lean Six Sigma, this is important because before we can improve a process, we need to make sure everyone agrees on what process we are actually studying. Now let's look at a SIPC diagram for the bearing housing example. We begin with the suppliers. In this example, the suppliers include steel vendors, tooling suppliers, and the maintenance department. These groups provide the materials, equipment, and support needed to keep the process running. Next are the inputs. The inputs include the raw steel material, CNC machines, cutting tools, and machine operators. These are the resources required to manufacture the bearing housings. The process itself is shown as a simplified sequence of major steps. First, the part is machined using CNC equipment. Then the part is inspected to verify dimensions and quality requirements. If defects are found, the part may go through rework. Finally, acceptable parts are packaged for delivery. The outputs are the finished bearing housings along with the inspection reports that document quality verification. Finally, we identify the customers. In this case, the customers include the internal pump assembly department as well as external industrial customers who will ultimately use the finished product. This example shows how a SIPC diagram provides a clear, high-level view of an entire manufacturing process. It helps teams understand where materials come from, how the process flows, what outputs are produced, and who depends on the final results. Root cause analysis is a systematic approach used to identify the true underlying causes of problems rather than simply treating the symptoms. In quality engineering and Lean Six Sigma, the goal is not just to fix a defect once, but to understand why the defect occurred in the first place so it does not continue happening. Several common tools are used during root cause analysis. Two of the most widely used are fishbone diagrams, also called cause and effect diagrams, and the 5 whys technique. These tools help teams organize possible causes and dig deeper into the source of the problem. Many root causes in manufacturing and industrial systems are related to machines, methods, materials, or people. For example, A machine may be out of calibration, a process method may be inconsistent, materials may vary in quality, or operators may not have adequate training. One of the key benefits of root cause analysis is that correcting the true root cause helps prevent recurring defects and repeated failures. This reduces waste, improves quality, lowers costs, and increases customer satisfaction. Instead of repeatedly fixing the same issue over and over, root cause analysis helps organizations implement long-term corrective actions that improve the overall process. Now let's look at a fishbone diagram for the bearing housing example. A fishbone diagram, also called a cause and effect diagram, helps teams organize possible causes of a problem into major categories. The problem, or effect, in this example is oversized bearing housing holes. One possible category is the machine itself. Tool wear or spindle vibration could cause the cutting operation to remove too much material, resulting in oversized holes. Another category is method. Inconsistent setup procedures may lead to improper alignment or incorrect machining parameters from one operator or shift to another. Material is another important category. Variations in the hardness of the raw stock material can affect cutting performance and dimensional accuracy during machining. Measurement systems can also contribute to the problem. Calibration issues with gauges or measuring equipment may cause inaccurate readings, allowing defective parts to pass inspection. The manpower category focuses on people-related causes. Insufficient operator training may result in improper machine setup, incorrect measurements, or failure to recognize process problems. Finally, the environment can influence manufacturing quality. Temperature variations in the shop may cause thermal expansion or contraction, affecting dimensional tolerances and measurement accuracy. This example demonstrates how a fishbone diagram encourages teams to think broadly about all possible contributing factors instead of jumping to conclusions too quickly. It helps organize brainstorming efforts and guides teams toward identifying the true root causes of quality problems. The Pareto principle, often called the 80-20 rule, is a very important concept in quality engineering and Lean Six Sigma. The basic idea is that a small number of causes are often responsible for the majority of problems. In many situations, roughly 20% of the causes may create about 80% of the defects, delays, complaints, or failures. Because of this, organizations want to identify the few critical issues that are creating the biggest impact instead of spreading resources equally across every problem. One of the main tools used for this purpose is the Pareto chart. A Pareto chart helps teams rank problems from the most frequent or most costly to the least significant. This allows improvement efforts to focus on the areas that will produce the greatest overall benefit. For example, a manufacturing company may discover that only a small number of defect types are responsible for most customer complaints. By correcting those major defect categories first, the company can achieve significant quality improvements much more efficiently. The Pareto principle supports data-driven decision-making because it encourages teams to rely on actual measurements and defect data rather than assumptions or opinions. In Lean Six Sigma, this concept helps organizations prioritize projects, reduce waste, improve customer satisfaction, and use resources more effectively. Lean Six Sigma is widely used in manufacturing to improve quality, efficiency, and overall process performance. It helps improve process capability by reducing variation and producing more consistent products that meet customer requirements. Lean Six Sigma also reduces downtime, scrap, rework, and other forms of waste, helping companies operate more efficiently and lower costs. Another important benefit is improved communication between departments such as production, quality, engineering, and maintenance. Teams work together using structured, data-driven problem-solving methods. It also promotes a culture of continuous improvement, where organizations constantly look for ways to improve processes and prevent defects. Overall, Lean Six Sigma increases customer satisfaction while also improving productivity and profitability. In summary, Lean Six Sigma combines quality improvement with operational efficiency to help organizations reduce defects, eliminate waste, and improve overall performance. One of the core frameworks used in Lean Six Sigma is DMAIC, which provides a structured methodology for solving problems and improving processes. Throughout this lecture, we also introduced several foundational tools, including Voice of the Customer, cost of poor quality, SIPC diagrams, and root cause analysis techniques. These tools help organizations better understand customer needs, identify process problems, analyze root causes, and prioritize improvement efforts using data-driven decision-making. As we move forward in the course, we will continue expanding on these concepts and applying them to real manufacturing and industrial examples using statistical analysis and quality improvement methods.